there is
Yanan,
still.
Excuse me, are you intending to share? We are not seeing your screen.
You mean?
We are not seeing your presentation. I don't know if you were supposed to share or not, but okay, now it's coming up.
I'm sorry, I don't know what's wrong with me. So
yeah, I got you.
Early, in Seattle, so
now we see the blue. We see the blue background, but your slides are off. There we go.
Okay.
Here we go. Super.
Start from the beginning. Yeah, I think I can start from the beginning. And yeah. So okay. So everything is good right now, right?
Yes.
Okay. Now let me start. The talk is about the deep speech, about deep learning system for domain specific speech recognition. Yeah, we will explore using pre-trained acoustic model and the semi-supervised annotator technique to create custom automatic speech recognition systems. Okay, and yeah, the human voice interface bring amazing advantages, including making language learning more convenient. But to achieve this, we need to build an automatic speech recognition system. However, to develop the ASR system, there are a few challenges. However, for example, we need to have large volumes of training data, and there are various factors that affecting speech signals, like the topics, the background noise, and the demographics, and all those features. The state-of-the-art ASR system have shown promising results. However, there is still a performance gap, especially for domain-specific speech in low-resource settings. So, okay. Well, in this presentation, I will be talking about how domain-specific ASR system can significantly improve performance in industrial applications. First, I will introduce a specialized dataset for ASR system development, and I will show a semi-supervised annotation method to tackle the challenge of acquiring annotated data. Next, I will present methodologies for improving ASR performance on domain-specific speech. Moving on, we will evaluate the performance of our ASR systems by comparing them to commercial ASR systems. Additionally, we will explore the use of error-prone ASR transcriptions in a benefit-specific natural language understanding task to assess their potential in improving spoken language understanding. Now, we will dive into the process of collecting and pre-processing the data for our domain-specific ASR systems. Specifically, we target data from a healthcare benefit call center known as BSCD, which focuses on helping and supporting customers regarding their company-provided benefits, such as health insurance. Our aim is to achieve significant improvement in ASR performance through the fine-tuning of acoustic models. However, fine-tuning still requires large volumes of high-quality annotated data. Manual transcription of such dataset is both time-consuming and expensive. Moreover, the manual process cannot guarantee error-free transcriptions, and the selected calls for annotator may not always contain benefit-specific terms, making them less useful for domain-specific fine-tuning. To overcome these challenges, we try to create an artificial dataset. First, we create a script of representative utterances by domain experts based on real users' chat and call data, and certain individuals with diverse backgrounds recorded the data in quiet environments. However, this process still proved to be time-consuming and labor-intensive. So, additionally, the recorded artificial data lack real-world variability. So the BSCD call center data provides a rich resource of benefit-specific acoustic data, covering diverse topics, demographic varieties, and noise conditions. So this enabled us to collect vast amounts of benefit-specific acoustic data, but they are not all unsupervised, with no correct transcriptions. To label this unsupervised data set with minimal human inventation, we propose a semi-supervised annotator method, which will be discussed later. Now, let's explore the pre-processing of audio data. When training acoustic models for speech recognition, we commonly use short utterances paired with transcripts. Long utterances are costly to process, so we split a lengthy call data set into shorter segments based on moments of silence. And to maintain consistency, all audio files, including call segments and recordings, they are all in the standard WAV format, and we resample them to match the training pipeline requirements. As we work with the utterance scripts used for fine-tuning the acoustic models, we need to ensure they align with the character inventory of the pre-trained models. This means our scripts should only contain alphabetic letters. And to achieve this, we apply a set of filtering rules to all the utterance scripts. Those filtering rules involve several transformations, such as convert all the target text to lowercase, eliminate the punctuation marks that are not pronounced in speech, replace abbreviations with their corresponding forward format. We also set some specific rules to handle numeric strings and symbols accurately. While converting scripts to alphabetic letters, mistakes can occur. For instance, the representation of the year may vary between 2023 or 2023. So, and inconsistent script representations lead to inaccuracy and hinder subsequent model training. To address this issue, we eliminate mistaken utterances using the semi-supervised learning annotation method. It helps refine the quality of the scripts and ensure the accuracy of subsequent model training. Now let's explore this innovative approach called semi-supervised annotation for data bootstrapping in ASR systems. This method enables us to leverage large unsupervised datasets and reduce system development costs. Semi-supervised annotator involves a process that enables us to bootstrap new data collections by relying on a combination of labeled and unlabeled examples. By utilizing this approach, we can overcome the limitations of relying solely on small supervised training sets. The semi-supervised annotation process consists of several components, shown in Figure 1. We start with a set of labeled examples here. Then employ a recognizer committee to generate rough transcriptions for a large set of unlabeled examples. Then after a few filters, a subset of newly labeled data is incorporated into the labeled examples for system retraining. The process is cyclic and iterative, as every step is repeated to continuously improve the performance of ASR system. In our experiment, we utilized DeepSpeech and Wav2Vec2 models, fine-tuned unlabeled data, and combine them with the AWS and the Google commercial ASR system to form a recognizer committee. This committee automatically generates rough transcriptions for a massive amount of unlabeled call data. To improve speech-to-text accuracy using this unlabeled data, we face two key challenges. First is to extract the valuable utterances from the large unlabeled dataset. Second is to identify the most accurate transcript from a set of rough generated transcriptions. Well, in the field of speech-to-text, we use two important evaluation metrics, the word error rate and the character error rate. The word error rate represents the percentage of words in the transcribed output that differ from the reference or grounded truth text. It calculates the overall word level error by considering substitutions, deletions, and insertions. A lower word error rate indicates a higher accuracy of the STT system. Character error rate, on the other hand, measures the percentage of characters that differ between the transcribed output and the reference text. It focuses on individual characters rather than entire words. And like a word error rate, a lower character error rate means better accuracy in capturing the spoken content. Well, these metrics allow us to assess the quality of transcriptions, identify areas for improvement, and compare different models or approaches. Well, in our proposal, we use a unique approach to assess the accuracy of our ASR system, the relative error rate. Since we don't have a traditional reference text, instead we have rough outputs from our speech-to-text systems. For each unlabeled audio file, X, and its associated rough transcriptions, we define relative word error rate, GKI, and the relative character error rate, GKI, by comparing the transcript generated from recognizer J as the reference text and the transcript generated from recognizer K as the prediction transcript. Here, J can be any one of the recognizers, and K can be any one of the other three recognizers in the committee. To evaluate the performance of the recognizer J for audio file I, we calculate the average relative word error rate and the character error rate. Then we normalize all the relative word error rate and the character error rate separately. Then calculate the weighted arithmetic mean to get the relative error rate for all the 4 ASR systems separately. And the true transcript for audio I is said to be the one with minimal relative error rate. This final label in our training data, they are mixed transcripts produced from all the 4 different recognizers. After we get a relative error rate for each audio file, we will set up an empirically determined threshold. If it passes the error rate threshold, we will select it to a subset for further processing. An audio file with a large relative error rate often indicates the presence of loud background noise, overlapping speech, heavy accents, or slurring. These factors, they lead to incorrect transcriptions. So to ensure accurate transcripts, upper threshold for relative error rates are determined empirically for each audio file. Furthermore, if an audio file has a relatively large relative error rate generated by the fine-tuned DeepSpeech or Wav2Vec models, it implies that these models have produced incorrect transcriptions. And we want to retain these audio files in the dataset as they represent areas that require improvement. So lower thresholds for the error rates of DeepSpeech and Wav2Vec are also established to ensure that all audio files in the training data contribute to model enhancement. Finally, utterances falling within the determined thresholds are selected to a subset. In addition to implementing an error rate threshold, we have incorporated a frequency detection to ensure dataset diversity and manage the number of similar utterances in the dataset. To further refine the dataset, we also have set constraints on audio duration and character lengths. The semi-supervised annotation approach has a major advantage. It relies on the transcripts generated by speech recognizers. This means we don't have to do manual transcription, saving us time and effort while reducing costs. The thresholds help us select high-quality data effectively, allowing us to build larger data sets through efficient bootstrapping. Next, we will discuss the acoustic models, language model, and the punctuation model employed in our ASR systems. The acoustic model plays a crucial role in speech recognition. Instead of training a powerful the acoustic model from scratch, we leverage the benefits of fine-tuning pre-trained acoustic models on domain-specific datasets. In our experiment, we utilize two popular open-source speech-to-text engines, DeepSpeech and Wav2Vec. DeepSpeech is constructed using a recurrent neural network trained with the CTC laws on a large labeled English speech dataset. Wav2Vec is a powerful, fully convolutional model trained on large amount of unlabeled audio data. It takes raw audio as input and generates latent speech representations, which are then processed by a transformer. In our experiment, we utilize three pre-trained Wav2Vec models, base, large, and large LV60. The base and the large models have different transformer configurations. The base model is smaller in size compared to the large model. The training data size for the large LV60 model is larger than the other two models. While these variations in model size and the training data contribute to diverse performance characteristics. Acoustic models can generate transcriptions at the character level, but they may contain errors, such as phonetically similar word substitutions or misspellings. So to boost ASR system performance, we integrate external language models, KenLM model, trained on domain-specific text. By utilizing the trained language model to decode the acoustic model's emissions, we can refine the transcriptions and improve the overall ASR performance, especially in domain-specific applications. In addition to the language model, we also utilize a punctuation model to address the lack of punctuation marks and the capitalization in ASR, improving readability for both humans and the natural language processing tools. The punctuation model, built using a bidirectional recurrent neural network, focuses on restoring inter-word punctuation marks such as commas, periods, and question marks. In addition, we address disfluencies in the ASR output related to numbers and symbols. By leveraging fine-tuned DeepSpeech and Wav2Vec acoustic models, along with domain-specific language and punctuation models, we aim to achieve superior performance in speech recognition for employee benefit applications and improve the overall user experience. Now, I will present the findings of our experiment. Our primary objective was to assess the performance of fine-tuned acoustic models and language models on domain-specific audio data, which included both high-quality recorded artificial data and real telephone calls. Additionally, we evaluated the effectiveness of these speech recognition systems in natural language understanding tasks, especially intent detection. We compare the performance of different speech recognition systems on error-prone transcriptions. Let's now explore the experiment setup in detail. Our training data set consists of 57 hours of company internal call center and 1.8 hours of recording data. Using the semi-supervised annotation method, we filter the call center data to obtain 21 hours of call segments. The call segment data offers several advantages. It's easier to collect, covers a broader range of unique words, diverse speakers, and more words per audio file. This makes the call segment data more representative of real-world scenarios. Now turning our attention to the task set. It contains 95 recording and about 900 call segment audios, respectively. The call test data were randomly selected from our internal call segments, involving various utterances such as greetings and farewells. To specifically evaluate the performance of our speech system on benefit-specific audio, we created a subset of the call test data by handpicking all the call segments containing benefit-relevant terms. It allows us to conduct a focused evaluation of domain-specific speech. To ensure the accuracy of our evaluation, all test audios underwent manual annotation. 2 annotators transcribed the same audio file. A third annotator reviewed and selected the better one as the ground truth for calculating error rate. Now let's discuss the fine-tuning process. The 4 pre-trained acoustic models mentioned before underwent fine-tuning using the 23 hours of labeled speech data. We also trained a 5-gram language model on 10 million words of cleaned domain-specific documents. Now let's check the results. In table 2, we can see the relative improvements gained from 4 pre-trained acoustic models and external language models across 3 audio test sets. Our comparison is based on the word error rate and character error rate metrics. Switching from DeepSpeech2 to Wav2Vec model, we can see it improves the speech recognition performance. And for Wav2Vec models, larger pre-trained models lead to reduced error rate. And the external language models improve the word error rate for all fine-tuned acoustic models, with largest improvement for DeepSpeech and the Wav2Vec based model. And the Wav2Vec large LV60 plus the language model, it stands out as the best performing fine-tuned ASR output. So we utilize this model for the subsequent evaluation. The transcripts carried out by AWS and Google ASR Systems are used as reference for comparison. The commercial ASR outputs usually include symbols besides alphabetic letters for easy reading. But to calculate the word error rate, one human annotator follows the filtering rules discussed before and changes the outputs to alphabetic letters, only transcriptions. The word error rate of the best fine-tuned ASR outputs along with the 2 commercial ASR outputs across 3 audio files reported in table 3. For the general call test set, the AWS ASR system produces the lowest word error rate. But for the domain-specific audios, including the recording test set and the call benefits test set, the fine-tuned model outperforms the AWS ASR system, especially for recording data which contains many benefits-specific terms. Well, in speech input industry applications, we use spoken language understanding to meet user requests. Spoken language understanding involves performing natural language understanding tasks after speech recognition. ASR plays a critical role by providing the input for downstream NLU tasks. However, ASR transcriptions are not always perfect and may contain errors. These errors can have a significant impact on the performance of NLU tasks. In our experiment, we conducted a specific evaluation focusing on the intent detection NLU tasks using ASR transcriptions that might contain errors. In general, lower word error rate generally leads to more accurate intent predictions. However, it's worth noting that even if the ASR system does not perfectly transcribe the intent speech, the final intent result could still be correct if there is sufficient semantic information presented in the recognition output. Since the fine-tuned model outputs are alphabetic letters only, but the intent classifier model is trained on regular text data. The model output requires additional pre-processing. So the punctuation model and the reformatting described before are applied to generate formatted transcripts, then feed them to the downstream intent classifier. The task utterance intents are labeled by two annotators based on the transcripts. Without knowing context, some of the utterance intents are not clear and removed from the task data. Table 4 here displays word error rate and the number of correct intent predictions based on 3 ASR outputs, the AWS, Google, and the fine-tuned Wav2Vec model. The intent predictions based on the manual transcripts are also calculated as reference. For the recording task set, the intent prediction based on fine-tuned Wav2Vec outputs performs the best. For the call segment task set, AWS ASR output has the lowest word error rate, but its intent classification performance is the same as Wav2Vec. The number of correct intent predictions based on the formatted Wav2Vec output is even higher than AWS. In addition, the intent classification results between fine-tuned ASR and human transcriptions are very similar. Even though the domain-specific fine-tuned ASR transcriptions may have errors, they often contain enough accurate terms which are crucial to the meaning of the utterance. As a result, the intent classifier can still produce the correct intent. In summary, our goal is to create an advanced ASR system using common internal audio data. To achieve this, we fine-tune pre-trained acoustic models and employ semi-supervised annotation techniques. The aim is to outperform commercial ASR systems, especially for domain-specific speech. However, building the ASR system does come with a set of challenges. Fine-tuning pre-trained acoustic models still require a significant amount of supervised data to ensure reliable performance. Moreover, the accuracy of the acoustic model is highly sensitive to the quality of the training transcriptions. So at the beginning of the process, humans are needed to get high-quality training codes. In this experiment, recording data is used to initiate the process. It takes time and effort at the beginning, but the acoustic models can be easily refreshed and improved as the training data sets and the ASR system transcript quality increased with more iterations. Building an in-house ASR system brings several benefits. First, it ensures data privacy by protecting personal identifiable information, which is often present in call center data. By having control over the ASR system, sensitive information can be safeguarded. Secondly, when it comes to specific domain tasks, the fine-tuned ASR output outperforms well in spoken language understanding tasks, even with a higher word error rate. In addition, there is a significant cost reduction compared to employing commercial ASR systems, particularly for call centers with high call volumes daily. In conclusion, our Well, our work demonstrates that building an end-to-end ASR system using internal audio data is not only feasible, but also highly beneficial. As for further research, we plan to explore ASR in other languages, investigate the robustness of downstream natural language processing systems, compare performance with end-to-end spoken language understanding systems, and continuously improve the accuracy and the applicability of ASR systems. So, thank you for your attention. That's all my talk. Any questions?